So we've been looking at the hat check problem, which can be said more mathematically as counting the number of permutations of n that have no fixed points. Let's give that set a name. Let's call it d sub n equals the set of w is a permutation of n such that it doesn't have a fixed point, means w of I is not equal to I for any I. So we saw this as kind of a hard thing to count. Even when we were enumerating the list for like D4, we kind of had to go one by one, and it wasn't particularly systematic. Now, it was the case that we could probably come up with a recurrence relation for it, which is part of your homework, but it was still going to be really hard to come up with an exact formula. Part of the reason for that is this condition, that wi is not equal to I. Avoiding something is generally hard. It's much easier just to do something. So let's think if we can rephrase this set dn. Instead of in terms of avoiding something, can we say it in terms of actually doing something? So for that, we can take all of the permutations. So Sn is just going to be the set of w is a permutation of n. Well, we know what that is, and we know that the number of Sn is n factorial. That's something familiar that we've counted. So how can we think of Dn as the complement of Sn by some other sets? Well, think about this. It's saying don't fix I for any I. Okay, well, let's think about the opposite. Let's do fix I. Let's say Ai is the set of W is a permutation of n such that W of I is equal to I. Okay? First of all, let's just do a sanity check. Is that easier to count? Because if we haven't gotten something easier to count, maybe it's not worth doing. Well, sure, let's do this. What is the size of a sub I? Well, what have I done? I've said that I goes to I, just as a map. I haven't said anything about what happens to any other numbers, so I don't really mind what they do. So they're completely free. Among the n-1 remaining things, it's completely free, so this is just going to be n-1 factorial. That's convenient. Okay, this tells me that I'm on to something here. So how can I write dn in terms of the things that I want? Well, I know that dn is equal to the permutations that don't fix, so we're doing a complement, that don't fix 1 or 2 or 3 or all the way out to n. Okay, so don't fix any of them. And it's an or condition. So all I have to do is figure out how do I count this? And I know my answer will be n factorial minus the size of the union. Well, that's exactly what we were talking about before with this theorem. How do we count a union? We just count it by taking intersections instead. Okay, let's go back to our A's and let's ask ourselves, can we understand the intersections? Are those easier to understand? Well, what happens if we take AI intersect AJ? What are we saying? We're saying this is going to be the set of W in Sn such that W of I is equal to I and W of J is equal to J, and I don't really mind about the rest. Well, how many are the rest? There are n-2 of them. So what's the size of this intersection? Well, the size of the intersection is just n-2 factorial. That's actually great. It's great for a few reasons. So first of all, it doesn't matter what I and J are. It only matters that I took two numbers and fixed them. So now I can say something like, if I'm going to take the intersection of AI1 and AI2 and all the way up to AIK, the reason I'm thinking about this is because I'm looking at this formula. What am I saying? I'm saying, okay, I fix this guy and this guy and this guy. I fix K things, and I let the rest do whatever they want. So what do I get? I get n-k factorial. That's how much freedom I have. So now I know how to plug into this formula, and I can actually use this to get a formula for the derangements. So let's do it. So what is the size of fixing 1 and fixing, or fixing 2, all the way up to or fixing n? What is the number of permutations that have at least one fixed point? Well, by inclusion-exclusion, this is the sum from k equals 1 to n of -1 to the k minus 1. I'm just copying the formula at this point. The sum over all subsets of size k of AI1 intersect AIK. So now I'm going to take what I have here, which is I've just said, here's what this is. I can plug it in here. But keep in mind, it doesn't matter which of these guys I take. So here, I happen to know how many different ways can I take a k-element subset of the numbers 1 up to n. They're in choose k options for here. Okay, so what does that give me? That means that I'm going to get the sum from k equals 1 to n of minus 1 to the k minus 1. And then instead of the summation, I know how many terms I have. I have n choose k terms. How big is each term? Each term is n minus k factorial. Well, keep in mind, what is n choose k? It's n factorial over n minus k factorial. So we can simplify this. Might as well do that. This is the sum from k equals 1 to n of minus 1 to the k minus 1 n factorial divided by k factorial. Great. Let's get back to the derangement question. So what is the number of derangements? Well, it's equal to the number of permutations minus this amount that we've just found, which is the sum from k equals 1 to n of minus 1 to the k minus 1 n factorial over k factorial. But of course, we know what the number of permutations is. That's just n factorial. So we can factor an n factorial out. Over here, the summation doesn't depend on n factorial, so it just pulls out, and so we can factor it. So what do we get? We get n factorial 1 minus the sum from k equals 1 to n of minus 1 to the k minus 1 over k factorial. So now I can take this minus sign and just sort of stick it in there. And what do I get? I get n factorial. I want to do one more thing. This summation starts at k equal 1. This is the term for k equals 0. So this actually becomes the sum from k equals 0 to n of minus 1 to the k over k factorial. This is the formula for the number of derangements of n. Why is that cool? First of all, we got a formula is kind of awesome. But let's think about probability. What ratio, if you like, since we haven't quite done probability yet, what ratio of permutations are derangements? Well, for that, we just take the number of derangements divided by the number of permutations. That's an interesting amount. The idea here is saying, if I just take a random permutation, what's the probability that it's a derangement? Another way to say that is, if we're actually in a physical classroom and I randomly hand back your exams after a test, and I don't mind about who, what's the probability that no one gets his own exam back? And the answer is, of course, we just take this and divide by n factorial. So it's the sum from k equals 0 to n of minus 1 to the k over k factorial. What is that? That's e to the minus 1, right? This is the Taylor series for e, just truncated. So it's about a third. So about a third of all permutations are derangements.